G'day. Welcome to the Smart Energy Lab and Module 1 of probably about an 8-part series in designing a solar and battery storage system. It focuses very much on off-grid, but it can also be applied to on-grid. So a lot of these principles are transferable. But I've got to start off with saying that a big shout out to Victron Energy. Victron Energy have provided me, as you might see from behind, a lot of product for my training courses over the years, not just for this series, but over the years. So I will be focusing quite a bit on Victron equipment. Victron, by the way, Victron Energy probably make the widest range of renewable energy products you could get. Everything from load side equipment that controls, monitoring, charge controllers, inverters. I mean, they can take you from a camping system right up to a large scale, project. So, a homestead or something in those sort of realms. So yeah, it's a really diverse range of products, and it's great for learning about how to build a renewable energy system. So you can actually build a small training system on quite a small budget. So I'm going to start off today talking about the principles behind design of a solar battery system, and we're going to do this a bit of drawing here, a bit of a shout out to those other teachers online like Eddie Wu, link to Eddie Wu up there, who's the maths genius in Australia who makes amazing training videos on mathematics. I'm not that level at all. In fact, plus minus multiply and divide is about all you need for my course, but I will be using a drawing tablet and explaining stuff. So that's kind of, it's a classroom and we're in it together. So let's get started. So I'm going to draw this system from scratch. So let me just start up with a new page here. Okay, well, because we're doing a storage system, we're going to make a solar and battery system DC coupled. Now, if you haven't heard the terminology DC coupling was the only way to charge a battery. You had a solar panel, you connected it to a battery, and current flowed, and you charged the battery. It was the oldest system, and it's still very, very viable and has some distinct advantages still. But it's also one of the simplest. And so if you're looking at a very small, simple system as what we're doing today, DC coupling is certainly the way to go. Now, it all starts with understanding what your objective is. And I say often the hardest part of designing a system is knowing what the energy load requirements will be. Now, I'm proposing what we build here is a small solar battery system to run a small fridge, something like your little portable camping fridges that you can run off either AC or DC. So we're going to build a small system for a fridge and work out what size solar panel and what size battery we need to keep the goods inside that fridge cool. So starting with number one being the load energy requirement. So what we're doing here is sizing solar and battery. Okay, so solar and battery system. And step one is the load. So how do you find this out? Well, there's a bunch of ways you could find out what the load energy is. You could actually use a power meter. In fact, that's what I've done here with the small camping fridge that I've got here in the studio. I just plugged a power meter into it and left it running for a day or two, and it tells me the average daily energy consumption. So I know that it uses 400 watt hours, and that's going to be our load energy design. So first we start off with load energy requirement, and that's in this case a small fridge, and it's in watt hours per day. Okay, so watt hours per day, that's our requirement there. So and we know that in this case it's going to be 400. So I'm just doing this in red. This is for our worked example. It's 400 watt hours per day. How did I find that out? I measured it with a power meter, but the other ways that you could do this is looking at the spec sheet for the product, and if it tells you what its power demand is and you know how long it's going to be running for, that's quite a good way. I mean, the case of a fridge is a bit more tricky because it'll be on, off, depending on the temperature of the environment. The duty cycle between on and off can vary quite a bit. So the manufacturer might be able to give you some stats on that. But if it's something like an appliance that you turn on, like a television, and it runs for, you watch it for 3 hours, then you turn it off again, you've got the power rating times 3 hours, will give you the watt hours. So if it's drawing 100 watts for 3 hours, that's 300 watt hours. The third approach is, let's say you're doing a bigger project, you're going to take your whole house off grid. Wow, that is a big project. You probably already have an electricity bill, and on that electricity bill, it'll tell you in kilowatt hours per day what your energy consumption is. Now, beware that it'll vary throughout the year, and you'll probably want to look at which is the toughest time of the year to create a solar battery system. Now, I'll mention this a few times, but it's called the load resource ratio. When is the resource, in this case solar, the sun, that has the worst ratio of energy to what the loads require? Now, in temperate climates like here in mountain or semi-alpine, subalpine Victoria, where it gets down to about 0 in wintertime, we've got not a lot of sun in winter, but we're also short days, indoors more, and there's more appliance use. So actually wintertime is the worst load resource ratio for us. And so that's where we'll be designing it for. So if you're using an electricity bill as a estimate of your load energy requirement, make sure that you choose a suitable period for the load resource ratio. So if you're in the tropics, it might be the wet season. If you're the temperate climate, it's more likely to be wintertime. But then again, you might have some special loads. You might do a lot of air conditioning and a lot of pumping in summer, and that may well make it the worst ratio. All right, step 2 is to decide what battery voltage we're going to have. Now, the reason that we actually put in battery voltage at this point is because we need to know for mathematics what the battery voltage will be. And I'm going to use, because this is a very small system, a 12 volt battery. So the battery voltage is going to be 12 volts. So there we go, 12 volts. Now, just being aware that that's a nominal rating. It's really a terminology from lead acid battery days, because lead acid batteries came in 2 volt cells. And so you'd put them in series to get, in the case of 6 in series, you'd get 12 volts. Though often for a small battery, they would be inside one case, what's called a monoblock. So you might actually have a 12 volt lead acid battery, but inside is 6 2 volt cells. If you're using, say, a more modern, like a lithium-ion battery, they have different cell voltages, and depending on how many cells in series, they'll be somewhat higher. So they might be up around the 13.5 to 14.5 volts nominal. So make sure you choose the right nominal voltage. But I'm assuming we're using a lead-acid battery here, and so we're going for 12 volts. Step 3 is allowing our system design to accommodate the losses. And we're going to do this in 2 parts. We're going to do first the load subsystem efficiency. Now, what I'm talking about here is the fact that we've got energy going into a battery from the sun, and then we're taking it out again. And so there's a round trip efficiency factor, energy out over energy in. And that's going to tell us what our efficiency factor is. So a factor, by the way, if you're not familiar with this terminology, is a kind of mathematically more simple way to calculate collectively a lot of efficiency factors together, because you just multiply them. So for instance, if you have something that's 100% efficient, its efficiency factor equals 1. And if it's 95% efficient, its efficiency factor is 0.95. Okay, you get me there. So let's have a look at what some of those losses are. Now, the main one would be your round trip efficiency of your battery. So we're going to put in there here, battery round trip, and that will depend quite a lot on what the chemistry is. So round trip. And then we'll have wiring losses. Now, wiring losses, I like to call them self-inflicted, because you choose the cable, you choose the loss. We can calculate exactly what that is, but in this case, I'm just going to fall back on the principles in ASN ZS 3000, which is a maximum of 5% voltage drop, which actually is power loss over a cable, over to the most distant part of a circuit. So I'm assuming a maximum of 5% for wiring losses, and then we've also got any conversion losses from DC to AC. Now, I did say this was a DC fridge. but we might be running it off an inverter. So let's just do that for a little bit of experiment. We're going to use an inverter. And so we've got some AC losses on our inverter. So AC losses on the inverter. In fact, what we're going to refer to those is the inverter's efficiency factor. So let's put some numbers in there. I'm going to, in red here, so we've got a lead acid battery. Now, lead acid batteries aren't that efficient. So about 85% round trip efficiency. And we're going to multiply that by our wiring losses, and I said we're going to use the principles of ASNZS 3000. So 5% wiring loss is 95% efficiency, or an efficiency factor of 0.95. And lastly, we're going to allow for an AC inverter that takes the 12 volts DC, inverts it to AC, and battery inverters particularly, are not as efficient as solar inverters. You might see numbers in the high 90s for solar inverters, but a battery inverter has a tougher job to do. It's taking an extra low voltage, like 12, and making 230 volts AC. It's usually got a transformer in it, so there's a bit more loss involved. So I'm saying 92% efficient, or efficiency factor of 0.92. Now this is when we crank out our calculator and do a little bit of multiplication. So we're going to go 0.85, which is the round trip efficiency of the battery, times 0.95, which is our wiring efficiency, times 0.92, which is our inverter efficiency. And that gives us an overall subsystem efficiency of 0.74, or in other words, 74% efficient. Of the energy that we put into the battery, 74% of it is actually usable by the loads. Okay, we're doing well. Now we're going to calculate the amp hour demand from that battery. So amp hour demand, by the way, it's amps times hours, it's not amps per hour. So amp hours, written usually as one word or sometimes hyphenated, on a daily demand. So the amp hour demand on a daily basis is simply dividing the first three sums together, so which is our capacity of our battery, our energy demand, which is 400 watt hours per day, divided by our battery voltage, which is 12 volts, and divide that by our subsystem efficiency factor for on the battery side, which is 0.74. Oops, get that right, 0.74. So that's going to actually tell us how many amp hours per day we're going to draw from that battery. So cranking out the calculator again, 400 divided by 12 divided by 0.74 equals 45 amp hours. So 45 amp hours per day are coming out of that battery to run this fridge. And that's via a small inverter. All right, we're nearly there. So that's step 4 of only 6 steps. I told you this wasn't really rocket science. Well, I didn't, but I am now. So let's go to the next step here, where we add a solar PV system. Now this is, you can get a bit more complicated here, but I'm going to keep it pretty simple. So step number 5 is understanding the amount of PV or solar panels we need to replace the energy we use and replace the losses in the system. So we've got to include the losses on the generation side, which is the solar panels and connected equipment, and the losses on the load side, such as the battery round trip efficiency, etc. So we start off with energy demand, and we know what that is already, and we divide that by our peak sun hours. Peak sun hours is a sort of industry shorthand for kilowatt hours per square meter of solar radiation. Now, it may be news to you, but there's a certain amount of energy falling on the planet, and it can be averaged on a monthly basis quite accurately, because the solar resource doesn't change dramatically from year to year. You might have a wet year and a dry year, but it's surprising how similar the solar resource on a monthly basis is. Now that data is something that, depending on where you are in the world, you may be able to get from your meteorological services. Here in Australia, the Bureau of Meteorology provide us with horizontal data. That's really only good if your panels are perfectly flat. It will be better as you incline them. There is some commercial tools out there. I might put a link in the description, some of the ones that are available. Some are free with limitations, and some are commercial with for those who do this professionally. But in a nutshell, we're going to design the system for where I live here at Mount Tulibuong in Victoria, just in the Yarra Valley, where it's pretty cold in winter. It's also not very sunny. So in wintertime, the sun dips down in the sky, so it's a lower angle. It's a shorter day, and the amount of energy falling on a surface is quite significantly less than summer. In fact, 1/3 of what it would be in summer. So it's going to be our design month. As I mentioned, wintertime in temperate climates often is the toughest load resource ratio. So here, using the data I've got from the Bureau of Meteorology and a bit of mathematics, we've calculated that there's 2.7 peak sun hours falling on a surface for a incline angle of 50 degrees. That's pretty steep. Facing true north. Now that's the best it can be in the middle of winter on a monthly average in June. 2.7 peak sun hours. So just remember that number. Then we're going to divide it by the PV subsystem efficiency. Now, we talked about the load subsystem, but now we've got to consider the losses on the PV side. Now, when you buy a solar panel, it might say 200 watts or 300 watts on the nameplate, but you won't get those watts out of that panel unless it's under very special conditions, basically freezing cold and 1,000 watts per square meter of solar radiation. The reason why it needs to be freezing cold is the panels are going to heat up, and they're tested at the cell level at 25 degrees Celsius. You put a panel out in the sun with 1,000 watts on it, it'll heat up 25 to 35 degrees above ambient. So the ambient would have to be down to around 0 to be close to the nameplate rating. So we're going to have thermal losses in our panel, even here in wintertime, where it might be 5 degrees outside in the morning, it might get up to about 8. We're still going to lose some power from our nameplate rating of our panels. We're also going to lose some in the DC cables that go from the panels to our charge controller and from our charge controller to our battery system. There's also other factors you can consider, such as shading, but we're not going to do that. Today we're going to assume that you put it in an unshaded location. Also, dust and dirt is another derating factor. It's pretty hard to really do that scientifically, but you could just assume there's going to be some losses due to dust and dirt. Many people use a default figure of 5% losses for dust and dirt. Anyway, we're going to package that up into a single figure for PV subsystem efficiency. And so I'm just going to write here PV system efficiency, and it's going to be 90% efficient. So of the nameplate rating in wintertime, about 90% of that energy is going to be produced from the panels. And lastly, we divide by what we've already calculated, our load subsystem efficiency and factor, and that will give us the number of watts of panels that we need. And this is kind of where the magic happens. So we know that our energy demand is 400 watt hours per day, and I've got a peak sun hour on a monthly average in wintertime here in the Yarra Valley of 2.7 peak sun hours. Now, I should point out that you'll have good days and bad days. So when you get a monthly average, it assumes that you are averaging over a weather cycle. And you'll see in a minute why having a certain amount of storage over several days helps with this design, because you're allowing for, the good days to catch up from the bad days. So that's a monthly average, that 2.7. So then we divide it by our PV subsystem efficiency of 0.9 and our load subsystem efficiency of 0.74. And that's going to tell us how many watts of panels we need. What I call the nameplate rating. So get the calculator out. 400 divided by 2.7 divided by 0.9 divided by 0.74 equals, you ready for it? 222 watt panel. That's all we need, 222 watts. Wow. Now I'm going to put a little P at the end there just to remind myself it's the nameplate rating of the panels. They're not real watts, they're peak watts or nameplate rating. You probably can't buy a 222 watt panel, so maybe the next step up. So you always got to scale up from there. And by the way, there is some benefit in oversizing your PV. Really, it helps in lots and lots of ways. I'm going to use what I call a design period of 5 days for my battery system. That means it can last 5 days without solar input, but that's quite a long time, and that makes for a bigger battery. But if I had more PV, I could recover quicker and probably need a smaller battery. But we're sticking with design principles actually from an Australian New Zealand standard, AS NZS 4509 Part 2, or Point 2, sorry. So 4509.2 has been around for over a decade or more, actually about 15 years, and but it's a good standard. It's not so good with AC coupled designs, but we're doing a DC coupled design here. So battery system sizing is our last step. So battery system size. How big a battery system? It may well be one battery, or it may be multiple batteries to achieve that capacity. So we already worked out that we needed a certain amount of battery capacity, amp hour capacity per day of 45 amp hours per day being drawn from our battery system. So we're going to start with 45 amp hours of daily amp hour demand, and we're going to multiply that by the number of days of autonomy. Now that terminology means the number of days without renewable energy input. So I'm going to choose 5 days. In fact, from the principles of ASNZS 4509, it recommends that you use 5 days if you don't have an auto start generator for backup. But ultimately, you can make this decision based on your usage characteristic. Let's say this is an RV vehicle that you only go camping on the weekends and you're only going to spend 2 days away. You don't actually need 5 days of autonomy because you're only going to be away for 2 days and then you're back at home and the fridge is probably plugged into mains power. Then we're going to divide it by the maximum depth of discharge. Now the maximum depth of discharge is dependent on the cycle life of a battery and the manufacturer's rating. This being a lead acid battery, I'm going to use a 50%. It's a conservative number, but 50% of my battery capacity is going to be used on a regular basis. Now, that's probably a safe number to use, certainly if it's a daily cycled system, that over the period of 5 days, you use 50%, which would be 10% per day. 10% of the capacity of the battery is taken out every day for 5 days, but you've still got 50% of the nameplate rating of that battery capacity left. But if this is an RV vehicle, really, you could probably go deeper than that because you're not needing a really long cycle life, because you're not going to cycle it much. You know, it's not going to be used every day, this vehicle. So really, maximum depth of discharge can be extended depending on the expected number of cycles that battery is going to have to deliver. So just going to solve that sum, and let's see what our battery capacity is. So we'll take 45 amp hours, multiply it by 5 days, and divide that by 50% maximum depth of discharge, and that tells us we need a 450 amp hour battery. Whoa. Okay, so if you're not familiar with what that looks like, that's a pretty hefty battery or batteries. You're probably looking at something like up here we've got a 220 amp hour battery from Victron. I'm going to show it to you actually. Yeah, so I'm pretty strong, aren't I? No, this is just a dummy. Normally this would weigh like 40-50 kilos, but this is a on the front here, it's giving us the amp hour capacity at 12 volts, so 220 amp hours. We need 450, so approximately 2 of these will give us 5 days of autonomy for our fridge, allowing for all the losses, and then it can recharge from a 222 watt panel. We probably could put in a 250 watt panel just to be sure. So that's how we convert a battery capacity that is smaller than what we need by having multiples. Now, I should point out that having multiple 12 volt batteries in parallel does come with some challenges. Personally, I would avoid it if possible. I'd probably not go beyond 2 in parallel unless I had a management strategy for the differences in those parallel strings. But yes, you can do it. So there we go. We've just gone through the process of designing a solar and battery storage system to run a fridge for continuously from a solar panel all year round. So even in winter when the solar resource is at its lowest. So thanks for watching, and look forward to the next explainer on solar and battery storage systems. Okay, see ya.